Bismillahirrahmanirrahim. Solution of ODEs by Laplace Transform. We learn the Laplace transform of functions in differentiation and differential equation, derivative of a function. So we will use the Laplace transform now to find solution of ODEs. So let's start with a simple equation. We have a population equation. So I am writing this equation. Let's say 2y is a population equation, and with the initial condition to be this. Now we want to use the Laplace transform to find the solution of this equation. So apply the Laplace transform. Okay, so I'm writing this on this side, minus 2 Laplace transform of y equal to 0. So we know that the Laplace transform of the derivative of y is s time Laplace transform of y minus y at 0, and this is only for this term. Now minus 2 Laplace transform of y equal to 0. So this implies when I take the Laplace transform of y common, I get s minus 2, and initial condition y at 0 is minus 1, and that is 0. So this implies that Laplace transform of y is equal to 1 over s minus 2. Now we got that y Laplace transform of y is equal to 1 over s minus 2. Now we will take the Laplace inverse of this equation. So Laplace inverse of Laplace transform of y is equal to Laplace inverse of this function. And we know this is the exponential to t from the previous knowledge. So this should be the solution. Y of t is equal to e to t. So this is the solution of the required equation, and you see the Laplace transform first convert this differential equation with this initial condition in this algebraic equation. You see this is an algebraic expression, and then we take the inverse of the Laplace transform and get the answer. Let's solve this equation again with non-homogeneous term. Y dash minus 2y is equal to t. Solve this equation y at 0, 1. This equation using the Laplace transform. So we again apply the Laplace transform of y dash minus 2 Laplace transform of y is equal to Laplace transform of t. So this give me s time Laplace transform of y minus y at 0, and then minus 2 Laplace transform of y for this term, and we see that the Laplace transform of t is 1 over a square. So we write this again on this slide. We take the Laplace transform of y from here and here common. So take the common, y of s common, we get s minus 2, and y at 0 is minus 1 is equal to 1 over s square. So overall we get ys equal to 1 plus 1 over s square. Oh, and here is the s minus 2 factor. Now dividing by this s minus 2 both sides, we get Laplace transform of s is equal to 1 over s minus 2 plus 1 over s square into s minus 2. Now we have to split this term by partial fraction. So this term s square into s minus, name this equation as equation 1, s minus 2. So by partial fraction we do this way, a over s, b over s square, and c over s minus 2. So taking the LCM and multiply this equation with the LCM, we get 1 equal to a s into s minus 2, b s minus 2, and c s square. So when we take s to be 0, s is arbitrary, so we can put it 0. So for that I got 1 on this side, and this is 0 and this part is 0, and we get here something, and that is minus 2b. This implies b is equal to minus 1 by 2. For s is equal to 2, this term and this term is 0, and we get 1 is equal to 4c, and this implies that c is equal to 1 over 4. Okay, now comparing the coefficient, we see that a square is here and c square is here. So the square coefficient is a plus b on the right side, and the left side it is 0. But we know b is minus 1 by 2, that is 0. So that means a is equal to 1 by 2. Okay. So a is equal to 1 by 2, b is equal to minus 1 by 2, and c is equal to 1 over 4. Okay. Now we split this term into these three terms. For a is equal to 1 by 2, b is equal to minus 1 by 2, and c is equal to 1 by 4. So I'm rewriting this equation again on the next slide. So this is equal to uh, why this is not working now. Okay, so let write again that equation. Capital Y of S is equal to, here is 1 over S minus 2, and here is 1 over S square into S minus 2. So we split this into three parts. So the first part is as it is, and this term is equal to A is 1 by 2 S, and then here is b is I think is minus 1 by 2, so minus 1 by 2 s square, and c is 1 by 4, 1 over s minus 2. These two are like terms, so we will add them. So y of s, when we add these two terms, we get 5 by 4, 1 over s minus 2, and I am writing the square term first, that is minus 1 by 2, 1 over s square, and this term last, that is 1 by 2, 1 over s. Now we will apply the inverse Laplace transform on each terms. So this is 5 by 4 Laplace inverse on 1 is minus 2. Minus 1 over 2 Laplace inverse on 1 over is square. And then plus 1 over 2 Laplace inverse of 1 over s. Okay. And now you see this will be the solution y of t is equal to 5 by 4. This is exponential to t. Then here is 1 over 2 and then Laplace inverse of this function is t square. And plus 1 by 2 and Laplace inverse of 1 over s is 1. Okay. Let me check things. B is minus 1 by 2. That is correct. And A plus C. So I made a mistake over here. You see, this is C. So this is plus 1 over 4. 1 by 4. So this means this A is minus 1 by 4. Okay. Now we will correct correspondingly. A is here. This is A, and this A is minus 1 by 4. So this is minus 1 by 4. Here is minus 1 by 4, and this is minus 1 by 4. So this is the correct answer of the given problem. This is yt. I'm writing it again because of this thing. 5 by 4 e to t minus 1 by 2t minus 1 by 4. This is the solution of the initial value problem given over here, this equation. So the Laplace transform works. So we solved two first order differential equation by Laplace transform, and we will continue solving some higher order differential equation, homogeneous and non-homogeneous. Okay, thank you.